Welcome to this webinar of the Enterprise Neurosystem Group. Today, we are going to talk about an interesting way to use the system to reduce network bandwidth and processing required when downloading large amount of data over the network. And it will be given by the team from University of Buffalo. I'll now turn it over to the team members to introduce themselves and to do the presentation. Thank you. So go ahead.
Yeah, I'll just share my screen.
Go ahead, Suryakant.
Yeah, you can go ahead, Madhura. I'll be sharing the screen.
Hello everyone. I'm Madhura and I'm a master's student at University at Buffalo. And Lady Pranav, please go next.
Okay, I'll go ahead. Hi everyone. I'm Vineet Kalvegi. I'm a final semester master student here at the University of Buffalo, pursuing my master's in computer science. This December it will be when we're graduating, and this project was done last semester by all four of us collaboratively under a course called CC 611, that is Master's Project Development.
Hi everyone. So my name is Suryakant Joshi. So yeah, even I'm a final year grad student. So I'm pursuing CS in UB. So yeah, that's my.
Hi everyone, this is Pranav. I'm also a final semester graduate student here at the Computer Science Engineering Department at University at Buffalo. That's about me. Thank you.
So today, the four of us, we are here to present our project, and the title of our project is Data Volume Reduction. We did this project as a master's project track, and we did it under our Professor Jinjun, and we were mentored by Dinesh and the whole ENG team. So thank you all of you because for all the help, and today we could make this presentation. So moving ahead. I'll give a brief overview of the problem statement. Today there exists a lot of data sets which are composed of artifacts, and the sizes of these data sets are very huge, like up to some lots of GBs and all. For example, if we take geospatial satellite imagery, the sizes of the data sets are very huge, and it becomes an overhead when for research and other purposes we need to work on this data and process it. So usually while working, we start with a smaller subset, and we need to for criteria of filtering so that we can get a small subset and only work on the necessary data and try to avoid or eliminate the unnecessary data. So most of the data sets have embedded metadata with it. So these metadata are usually files embedded in the original data sets, and they contain a lot of useful information which helps the user to determine what data they need and how to eliminate the unwanted data. Can you please move to the next slide? So, for example, the data sets that we had in mind while we were developing this project was the image files. So, for example, the GeoTIFF images and the XF images, these image types have metadata embedded in. So a lot of applications and machine learning and for various purposes, we need to work on images, and the data set being used, it becomes an overhead when we need to filter them, and that's why this is where metadata comes in handy. So data sets with image files, audio files, and other scientific data, they have if we get an access to the metadata, like this with the information which describes the data set, then it becomes easier for the user to just go through this metadata put forward the requirement, like what kind of and what relevant data they need, and then just wait on the filter the files, and then only download the required subset instead of like downloading the huge data set. So existing workflow right now is the like normally when we need to work on any data of any application and we require to perform some analysis and exploratory data analysis, we just download the entire data set from the repository and then onto the local system, and then like we manually write some script or write a code which will then pre-process the data, clean it, and according to the requirement, filter and form a smaller subset for us to work on. Normally the user downloads the entire data set on the local system, or they prefer they have to bring in some third-party software like AWS S3 buckets and all, which provides with SQL querying facilities, and then move this data from the source to the buckets and then process it and then get it to the local system. So this all this process is very tedious and takes up a lot of bandwidth, volume, and time, rather than the actual development and application. So with this project, we propose to introduce a standard API which will let the user explore the data set like through the metadata and the embedded information, and then only download the required data set without having to deal with the other unnecessary data. So in this project, we will explain the proposed API standards, the query standards, and the simulation which we implemented to show how this system would work. And yeah, so moving forward, my team members will explain these next details.
The workflow for legacy data provider. So this is the case like while we were actually implementing our project. So we faced a lot of issue that there are data providers which actually provide data set in a zipped format, in a compressed format, which is not very flexible. But then again, if you have to let's say be able to let the users choose from the metadata, so you would have to like as the data reduction platform, you would first have to download the data and then extract it, and then like build a metadata data set out of it, so that you can build filters on top of that and then provide it to the users. So we while implementation, we came across a lot of data providers which actually provide this, and this is quite popular among the data providers. So for such data providers, what we do is that as the data reduction platform, so we first of all get the data. So what our main idea to reduce the bandwidth would be to place the data reduction platform as near as possible to the data provider, so that bandwidth is reduced, and then the data like won't have to travel like far distances. And once we have the data in the data reduction platform, so we can again once we get the data, we extract the metadata and then build a sort of index on that metadata, so that we can build more filters on it. And again, as a part of our reduction platform, so after the user actually filters out, let's say like applies the filter, so we also implement a data compression engine, which is nothing but we put together all the entities that have passed the filter, and then we can pass it on to the user. And so this is a workflow for the legacy data provider. And but more what do you call, more advantageous would be to have the data provider actually store the data in the format that we want. So so this is especially very useful for let's say like if for example geotiff images. So like even one image is very huge. So if the data is kept in such a way that like every single entity can be accessed on its own, so that would make downloading and handling the data very easy. So in this is the version 1 of the proposed architecture that we propose in this project. And so the API standards, which we'll be going through next, so that is the standard that we expect the data provider to keep the metadata in. And this metadata, so since each entity has metadata of its own, so the data provider is expected to build the index that we use to build on the reduction platform. So our job would just be to query the data provider to get all the filters, and then once we get the metadata, we would again filter it out and then provide it to the user. Again, a more a more, let's say, logical extension of this idea would be to move the metadata filtering engine as well on the data provider, so that as a data reduction platform, we would just be responsible for letting the user explore the data in terms of providing him with a user interface, which is very interactive to like intuitive to use. And since the data is all on the data provider side, so this would literally minimize the transfer of data, like unnecessary transfer of data, so that the metadata is kept in the metadata is stored in the standard that which we require. And then since the filtering engine is also again located in the data provider side, so it would like literally reduce one round trip of the data. And then once the data provider has filtered the data, then he can again implement the data compression engine. But again, like since we would also require that each entity in these data sets be individually accessible. So what advantage this has is that the current issue we faced was we couldn't download entities parallelly, and making each entity accessible on its own, so will allow parallel downloads, and then it will make the downloading of the filtered dataset much faster. So what we propose, so as my teammate earlier mentioned, so we as the data reduction platform, so our main goal is to basically provide the user with an interface of which will mainly help him to explore the data in terms of how get a feel of the data and then filter it on the metadata, so that he doesn't have to deal with the entirety and then hog all his resources in that pursuit. So in this project, we have extensive, we support EXIF images, which is nothing but the PNG, JPG images, and like similar formats, and geospatial images, that is GeoTIFF images, which was a primary requirement. And we also for GeoTIFF images, we did find open source GeoTIFF S3 bucket, so which we have used for our implementation. And yeah, so our project mainly so the contribution, I would say, of the project that we make are we provide the metadata storing format for the supported datasets, that is GeoTIFF and the EXIF images, which we'll be going through in a bit. Provide APIs for the data providers for metadata retrieval, not just metadata retrieval, but again, if the data provider decides to go ahead with filtering and data compression, so we have provided APIs for that as well. We implement the data reduction platform. Again, the current implementation is basically this diagram, which yeah, this is the current implementation that we're doing. And the data provider, since we wanted to not only work with the legacy data provider, but again, we wanted to show how if our system design is accepted by the data provider, so we show how fast it will be, and hence we actually implement a prototype of the data provider. And again, as I mentioned, we support EXIF and GeoTIFF datasets. So the storage format structure. So the first one is this is like we expect a JSON structure again. This is the keys that have to be present in the geotiff images. So these are the primary, these are the main keys that they're very popular in the geotiff data sets. So as you can see, like 7, I think, one, almost around 8 are mandatory. So, and then the other 2 are optional. And again, we mentioned this is for the EXIF images. So again, all these keys have to be present. So uh, uh, let's say a random PNG image will have most of these metadata fields present in it, and the others which are optional. So they are depends on what source like what source is producing the image. Yeah, I'll pass it on to my teammate for covering the next part.
So I'll talk about the API standard that we plan to impose on the data providers in order to standardize the operations of retrieving the metadata and the indexing of the metadata. So as you all know, filtering the data using the embedded metadata of the artifacts is a powerful way to um, manage and organize these large data sets, the GeoTIFF and EXIF images. So in by using metadata to filter data, we can, it's possible to quickly find specific files or information. And this requires the data providers to actually have a unique identifier of each artifact or each file within their indexed metadata. If the if the file name isn't good enough, they could implement a UUID, a unique ID for each artifact, and embed that into the metadata, um, and index that along with all the other index metadata. So once this is done, as the data continues to grow in size and complexity, the data grows in gigabytes or petabytes, whereas your metadata would grow in kilobytes. So you would rather use that to filter first than have the overhead, have the bandwidth and CPU overhead of downloading and processing the entire binaries of the actual images. So we propose that the data provider expose an endpoint to each data artifact that will extract the associated metadata of the artifact and return it in a JSON. And more ideally, as Surya mentioned earlier, we propose that the data provider may also perform filtering on this metadata and return us the subset of the unique identifiers for each artifact, so that all we have to do is provide the interface for the users. Good. Next slide. And this is the documentation that we have developed that we would expect any data provider that would want to conform with the standard to implement. I'll give it a second to load. Yeah. So over here, we have separate post and get endpoints for both the data reduction and the data provider platform. So as you can see, the data provider endpoint is shared by both the data providers. Could you scroll down a bit? Yeah. The data provider uh, endpoints is shared by both the data providers and the reduction. This is in case certain data providers don't conform to the standard, and we would have to, and users would may still want to use that data source. So then what we would have to do is we would have to resort to a fallback where our data reduction platform acts as the data provider platform by actually going in that legacy workflow by downloading all the binaries. And this is done just as a fallback measure. But ideally, the data provider would have indexed all the metadata and return as the filtered subset. So yeah, so it's pretty detailed. We'll provide a link in the chat for you to go through later. But yeah, in a nutshell, that's basically it. It's separate endpoints that the reduction and the provider platform must both conform to in order to standardize this operation of indexing metadata and filtering upon it. We'll go to the next slide, Surya. Yeah. So this whole process of filtering can be distilled down to this abstract syntax tree where we uh, take each filter that resolves into a Boolean yes or no, true or false, and combine them together using and or operators. So it's similar to how you would chain any relational operators in in your favorite programming language, so Python or Java, for instance. So go to the next slide. Yeah. So this is an example of like text filters being combined together with separately with and or operators, and this is the tree we've built up using a JSON that we'll see soon. So what this does is it's pretty simple. Um, each individual filter gets resolved into a Boolean, and they get then passed on to the operator above them, which is then resolved into another Boolean, and so on until you reach the root. And if all of these filters resolve into a Boolean true, then that individual artifact has passed the filter, else it hasn't. And the beauty of this is each we've displayed simple individual filters such as like a string that starts with that ASP underscore LIT, or a string that is perfectly matching with the string EPSG, or an integer or a Boolean or an integer or a floating point that we perform um, equality lesser than greater than operations on. In addition to this, we can also implement custom filters. For example, for the geospatial images, we can implement, say, bounding box intersection. The user could provide a latitude and longitude pair, and we would check if the geospatial image if that latitude longitude point is contained within the bounding box provided by the artifact. And we can check that for all the images, and that could be a filter of its own. And that would fit very neatly in this abstract syntax tree as just another leaf that could be ANDed and ORed, as you can see right here. So, and taking that syntax tree, we can represent that in a JSON format where we have an array of filters where uh, each um, where each filter is we have filter groups and filter objects. Each filter group is I'm trouble recollecting. Could you help me with this, Surya?
Yeah, so each filter in this is ANDed together, and then the first list, as you see, so the first two filters are ORed together, and in the second list, so these two, like the compression and the code, they are ORed together, sorry, ANDed together, and then all the filters in one list constitute a filter group. So this the first is a filter group and the second is a filter group, and then we basically both or these filter groups together.
Right. Thank you. Yeah. And this is our what we have implemented as part of our demo. This takes in the legacy, because currently no data provider conforms to our standard. So we kind of simulate a data provider on our own reduction platform by by hosting two separate containers so that they kind of one kind of emulates the provider, and one would be the data reduction platform. So what we do here is we just have a copy of the data provided by the legacy data provider indexed in one container, and the other data reduction container would just read from that copy, uh, read the metadata from that copy and perform filters that are provided by that are specified by the user, and give the user a preview of the filtered subset. And once everything is good to go, the user can click download, and we would then query the subset from the copy of the data we have and send them right onto the user. And the stack that we have used is for the front end, we've used Next.js. That it's basically an extension of React.js, but it provides server-side routing. It's basically React.js, but with multi-page routing enabled. And for our backend, the REST API implementation, we've gone with Django REST API. And to represent and index the data, we've used the Pandas library. The Pandas library has been especially useful with its dtypes feature, where they automatically infer the data type of each of its attribute in a dataset. So that has been useful for us for the rudimentary filters. And we have deployed this as a containerized application on IBM Cloud. So that's the link to our live application, and I guess we will play a video of demonstrating the working of this hosted application.
Data reduction UI platform, the container on. Yeah, so in this demo, so this is a demo for the EXIF image. So like we have two working videos. So that is one for the EXIF and one for the GeoTIFF. And I am 1 second. Yeah, so sorry, this is for the EXIF images. So like basically this walks over like how it is deployed, what's going on in the backend, and then and how the user is interacting with you. So yeah, IBM Cloud Engine platform. Let's test the application. Let's start filtering, and we'll be handling EXIF images for this demo. This is a Kaggle's dataset URL, which contains images of pizzas or not, which is used for classification. And yeah, let's submit. And as you can see from the server logs of the data reduction platform, so it's downloading the image, and then it'll basically construct a metadata data frame from this. So till that time, we will be showing loading icon on the UI. So if I hit refresh now, and let's say we can view the metadata here of the EXIF images. So here, as you can see, you can preview the data. So right now, basically preview will give you the top, 12 random images, just to check out how your data set looks like. And then you can start filtering. So before filtering, let's see, make exposure. Let's choose a, so let's say I want to filter by artist this. Filter. Choose artist equal to, and so out of number of files, just 3 match the filtered criteria. Let's hit submit. Then you'll get a download button. And then let's save this. Let's check out the images. As you can see, these are the images that match the filtering criteria. Yeah. To again, the same process can be performed for geotiff images. So we also do have a demo of that as well. Yeah. Let us launch the application. We are again basically filtering out geotiff images from the geospatial dataset. These are the S3 buckets. So let me choose one S3 bucket. So when you are loading an S3 bucket, so this will basically appear as this. And so in the background, it has downloaded the dataset and extracted the metadata out of it. So let me hit refresh. So if you want to see the preview, so this is how the Sentinel COGS metadata would look like extracted from the images. Then you can also preview the dataset on how it looks like. So these are 12 random images picked up from the dataset to basically for you to get a better view of the data. So these are again, so once you go on pressing this will basically give you random images, 12 random images, so that you can get a better feel of how the dataset looks like. Then let's filter. Let's choose interleave as equal to this, and we have, let's say, band preview filter data. So for demo purposes, since the GeoTIFF images are very large, we just have 30 of them. And then after filtering, we end up with 28 of these images. So let's submit, and then let's download this. So now let's download the image, the filtered data. As you can see, we have all the 28 images that match the filter. And yeah, this is the final compressed file. Yeah, and back. Yeah, so that was for the demo, and yeah, so we are free for any questions that you guys have.
Thank you, guys. That was really interesting. Any questions from the audience? Any comments?
Yeah, I have